You open an app on your phone, nothing loads. No spinning wheel of doom, just empty silence where the internet should be. Somewhere between your thumb and a distant data center, an invisible machine has failed to assemble itself. That machine has a name in modern mobile networks. It is called a PDU session, a protocol data unit session. And without it, your phone is registered, authenticated, and utterly useless for data. Tonight, we follow the creation of that session end to end, a choreography of specialized network functions that must agree in the right order before a single packet can leave your device. What is at stake is simple. Either the pipe appears and video, maps, and emergency messages flow, or it does not, and the digital world stays locked behind glass. Think of a PDU session as a private tunnel your phone rents from the mobile network. Not a radio link alone, those come and go as you walk, but a lasting logical pipe that carries Internet Protocol packets between your device and a data network, the DN. After a phone finishes registration, it is known to the network. It has an identity. It does not yet have an address on the Internet, nor a path for user data. The session is the missing piece. In fifth generation systems, the user equipment, or UE, your phone, modem, or car module, asks the network to build that pipe. The network answers by selecting controllers, checking credentials, attaching policy, picking a forwarding engine, and handing the phone an IP address. Only then does data flow. Miss any step, and the tunnel never opens. Before the first message flies, meet the players. The UE is the impatient customer. The GNB is the radio base station, the tower side that hears the phone. The AMF, Access and Mobility Management function, is the front desk. It already handled registration, and now it routes session requests to the right specialist. That specialist is the SMF, the Session Management function, the conductor of this whole story. The UPF, User Plane function, is the freight yard that actually forwards packets. UDM and AUSF hold the subscriber's secrets and rights. The PCF writes the rules of the road, quality of service, charging, allowed networks. And the DN is the destination, the public internet, or a private enterprise cloud. Each speaks a different interface language. The drama is getting them to agree without the user ever noticing. The story begins the moment the UE decides it needs data. It builds a PDU session establishment request, a compact plea that names what kind of session it wants, which data network name it aims for, and hints about how traffic should be treated. That request rides over the radio to the GNB, then onward into the core, landing at the AMF. Picture a sealed envelope slid across a marble counter. The AMF does not open every detail of the session itself. Its job is triage and dispatch. It already knows the subscriber from registration. Now it must answer a harder question. Which session manager should own this pipe? Choose poorly, and the session lands on an overloaded node, or one that cannot reach the right data network. Choose well, and the rest of the orchestra can tune. Step 2 on the flow is SMF selection. The AMF weighs subscription data, the requested data network, local configuration, and load. It picks an SMF the way an air traffic tower assigns a runway, not at random, but for reachability and capacity. Then comes Create SM Context Request. The AMF hands the SMF enough identity, security, and session parameters to begin building state. Context here means memory. Who the user is, what they asked for, which radio access is involved, and which policies might apply. The SMF becomes the single brain that will coordinate authentication, policy, user plane setup, and the final accept message back to the phone. Until that context exists, there is no conductor, only disconnected instruments. Before any tunnel is carved, the network asks a cold question. Is this subscriber allowed to open this kind of session to this data network right now? The SMF turns to UDM and AUSF, Unified Data Management and the Authentication Server function. Together, they are the guardian of the keys. They hold permanent subscription records, authentication vectors, and service authorizations. Real world stakes are sharp. A stolen phone might still hold a valid radio attachment from moments earlier. A corporate line might be barred from public internet access. A prepaid account might have exhausted its data bucket. Authentication and authorization at session time catch those cases before an address is spent and a path is reserved. Only when the guardian nods does the flow continue. A refusal here is a clean no. Better a denied session than a leaking one. When checks pass, the SMF answers the AMF with Create SM Context Response. On paper, it is a simple acknowledgement. In practice, it is a contract. The SMF confirms it has accepted ownership of the session, stored the context, and is ready to drive the remaining steps. Failures surface here too. Unsupported PDU types, missing subscription, or resource exhaustion. So the AMF can tell the phone cleanly rather than hanging in silence. From this moment, the SMF, not the AMF, is the primary author of what happens next. The front desk has handed the file to the specialist. The specialist now needs rules, a road, and an address. Who decides whether this session gets premium latency for a video call or best effort bits for background sync? The SMF selects a PCF, the policy control function, and opens an SM policy association. Think of the PCF as the city planner for this one highway. It returns policy decisions, quality of service profiles, gating rules, charging keys, and conditions that can later modify the session when the user roams or a package expires. Association is not a one-shot stamp. Modification messages let policy evolve while the session lives. Throttle a heavy downloader, upgrade an emergency flow, cut off a delinquent account. Without this step, the network would know how to forward packets but not how to treat them fairly. With it, every byte travels under law. Policy is ink on paper until someone actually carries the freight. The SMF selects a UPF, the user plane function, the element that will receive packets from the radio side and send them toward the data network, and the reverse. Selection cares about geography, capacity, and which DN the user requested. A UPF near the user cuts latency. A centralized one may simplify enterprise breakout. Next, UE address allocation. The phone still has no IP address for this session. The SMF, sometimes with help from the UPF or an external server, assigns one. IP version 4, version 6, or both. That address is the phone's identity on the far side of the tunnel. Without it, applications have nowhere to bind. With it, sockets can open. The superhighway now has an on-ramp labeled with your number. Selecting a UPF is not enough. The SMF must program it. Over the N4 interface, the SMF installs packet detection rules, forwarding actions, quality enforcement, and usage reporting. In plain language, if a packet matches this session's identifiers, send it this way, mark it with this priority, and count the bytes for charging. This is the moment abstract policy becomes concrete machinery inside a packet processor. Get N4 wrong and traffic black holes. Packets enter and never leave. Get it right, and the UPF becomes a disciplined courier that already knows the destination DN and the return path toward the radio. The control plane has finished whispering instructions. The user plane is armed. The core still has to tell the edges what was decided. The SMF triggers an N1-N2 SM message transfer through the AMF. N1 is the signaling channel toward the UE. N2 is the channel toward the GNB. Together they carry session parameters the phone and the radio need. Quality dash of service flows, tunnel endpoint identifiers, security parameters for the user plane, and the PDU session accept contents. Imagine two sealed briefings leaving headquarters at once. One for the driver, one for the toll booth. The phone learns its new address and rules. The base station learns how to map radio bearers onto the core tunnel. Until both are configured, the middle of the network is ready and the edges are blind. Now the radio and the device do their physical work. UE and RAN, resource setup, allocates the air interface bearers and radio resources that will carry this session's packets. In parallel, the PDU session establishment accept reaches the UE, the network's formal yes. It confirms the session identity, the negotiated parameters, and the assigned address. Applications waiting on connectivity can finally proceed. This is the audible click after a long silent handshake. From the outside, it looks instantaneous. Inside, 11 coordinated steps have completed: request, selection, context, authentication, response, policy, UPF choice, addressing, N4 programming, edge configuration, and resource setup. Only then is the accept honest. And then data flow. Packets leave the application, cross the radio, enter the GNB, ride the tunnel into the UPF, and exit into the data network toward servers across the planet. Return traffic mirrors the path. The PDU session is no longer a diagram. It is a living pipe with policy on its walls and an address on its door. Scale the picture. A stadium powers on 30,000 phones after a goal. Each may trigger this flow within seconds. The same choreography that saved one frustrated user must hold under flood without confusing sessions or leaking another's traffic. Reliability is not a slogan here. It is whether the accept still means what it says when the city lights up at once. Remember the silent screen at the start? That emptiness was not mystery. It was a PDU session that had not yet been born, or one that failed midwife. Understanding this flow turns outage into diagnosis. Is the AMF failing to select an SMF? Is authorization rejecting the data network name? Did N4 never program the UPF? Did the accept never reach the phone? Each question points to a named step and a named function. What this knowledge made possible is deliberate engineering. Slicing networks for factories, steering video through nearby breakout, enforcing enterprise policy on private 5G, and recovering faster when something breaks. One question still hangs over the field. As billions more devices, sensors, vehicles, industrial arms demand sessions that are not only connected but always secure, always low latency, and always available, can this same careful dance stay fast enough and safe enough without ever asking the human to notice it at all? The pipe is open. The next failure will teach us whether we truly understand why.